Thank you, Perla. First, would like to thank the organizers for this invitation. And so I'm going to talk about local times of Brownian motion indexed by the Brownian tree. I think this fits well in the topic of the conference because there will be occupation fields, well, there are densities, which are local times, maybe some scaling limits also. And I could have spoken about random geometry too. It's very much related to what I'm going to speak about. Okay, so let me outline the lecture. So I will spend some time in the first part of the lecture describing very classical facts. I'm sure many of, maybe almost all of you already know that, about excursions and local time of linear Brownian motion. And the reason for spending some time on that topic is that I'm really going to be talking about analogues of these classical results in a more complicated setting, which is the setting of Brownian motion indexed by the Brownian tree. So I will introduce that in the second part of the lecture. So then I will discuss local times for this tree-indexed Brownian motion. And what I'm interested in particular is the Markov property of local time. Okay? And the tool to study local times is excursion theory, and I will also explain what I mean by excursion theory for this Brownian motion indexed by the Brownian tree. And in particular, I will state the key lemma that gives the Markov property of local times. Okay. Then the next part, I will show that local times satisfy a certain stochastic differential equation. Okay? And I will also explain how we can obtain this stochastic differential equation. And in the last part of the lecture, I will maybe give some ideas of the proof of the key lemma. Okay, so this is the outline of the lecture. So let me start with very classical facts. So you can consider here standard Brownian motion, standard linear Brownian motion starting from 0, for instance, Bt, and we can define its local time process at 0, measuring the time spent at 0 if you want by your Brownian motion. And we can also define the inverse local time, this tau s, which is the first time t when the local time at 0 becomes greater than s. Okay? And we have the following properties. So we know very well this process tau s here. Okay? As a process in S, this is a stable subordinator. Subordinator means increasing Levy process, but it's also a stable Levy process with index 1/2. Okay? And the reason for introducing this process is that you can use it to code the excursions. So more precisely, there will be a one-to-one correspondence between excursions of the Brownian motion away from 0. So by an excursion, what I mean is the part of the trajectory between, on a connected component of the complement of the 0 set. And so there is this one-to-one correspondence between excursions and jump times of the process tau s. Okay? The set capital D, the set of all jump times of tau. And correspondence is very simple. With every s belonging to this set capital D, with every jump time of tau, you associate the excursion between time tau s minus and time tau s. And then you can say that if you condition on this process tau s, well, the excursion become independent, and the conditional distribution of one excursion only depends on its length, its duration. It should be tau s minus tau s minus. There is a typo here. Okay. So this is just repeating what I was saying. This one-to-one correspondence between the jump times of tau and the excursions. And also you can describe the conditional distribution of the excursions. If you condition on the length of the excursion, tau s minus equals to R, the distribution of the excursion is this probability measure, which I denote here by NR, which is, if you want, the law of a Brownian excursion with duration R. And in fact, it's convenient to view this NR as a conditioned measure for a more basic underlying measure, which is the Ito measure of Brownian excursion, this measure capital N, so bold N, sorry, conditioned on the fact that duration is equal to R. So sigma will denote the duration of the excursion. Okay, so all these measures LR, the law of Brownian excursion with duration R, you can view them as conditioned measures of the Ito measure, bold N here. Okay, so I insist on that because I'm going to use this Ito measure in what follows. Okay? And you can also decompose the Ito measure, of course, as a positive part and a negative part. Okay, so let me come to local times now, and I will state it for Brownian excursion because this is perhaps more relevant to what I'm going to do later, but of course there are different forms of the Reinhardt theorem. So I consider a Brownian excursion under the Ito measure of positive excursion, is n plus, okay? And so I have an excursion with a random duration, already noted by sigma, and again I can introduce its local times. So the local time at level A, sometimes a measure of the set of times where the excursion is equal to A, and more formally, this is LA indexed by A, correspond to the continuous density of the occupation measure of the excursion. Okay. So the classical Reinhardt theorem tells you that this local time process evolves. Here I indexed by A positive. Maybe I will make a comment on that. This evolves like a squared Bessel process of dimension 0, or if you prefer, it solves a stochastic differential equation of this form. So dLA equals square root of 2LA times dBA, B is the Brownian motion. Okay? And in fact, here I'm arguing under an infinite measure, this n plus. But what you can do, you can look only at the local time, say for values of A greater than epsilon, and condition n plus on the fact that the excursion hits the level epsilon. And then you are arguing in the well-known, well, the setting of a probability measure, so everything makes sense perfectly. Okay, so that was a brief reminder of what we have in the classical setting for linear Brownian motion, and you will see the analogy in the results I'm going to state later concerning Brownian motion indexed by the Brownian tree. Okay, so roughly speaking, the goal of the lecture is to present analogous results to those I have just recalled, but in a different, slightly more complicated setting, Brownian motion indexed by the Brownian tree. So what is this object? Okay, so I start with the Brownian tree, and well, there are many different ways of defining the Brownian tree, but for me, it will be convenient to view it as a tree coded by a Brownian excursion. So under the same measure I was considering before, this Ito measure of positive Brownian excursions. So under this measure, you have a trajectory like this, an excursion away from 0 with duration sigma here. And you can associate with this excursion a tree. So I call E the excursion. The tree will be denoted by TE for the tree coded by E. And how do we get the tree? Well, essentially, we are going to draw all horizontal chords below the graph of the excursion. So these are all the red chords here on my picture. I've drawn only a few of them, of course, infinitely many of them. What I'm going to do, I'm going to identify 2 points which are endpoints of one of these chords. Okay? So for instance, this point here is going to be identified to this one. So you should imagine that your graph is a strip of paper, if you want, and you glue 2 points which are at the same level on the graph below the graph. Okay? You glue 2 points which correspond to the endpoints of a chord below the graph. Okay? So this is what is going to give you a tree. So maybe I should be more formal. This was a very informal definition, but the formal definition is as follows. You say that 2 points S and T in 0 sigma are equivalent if you have this property. The excursion at S is the same as the excursion at T and coincides with the minimum of the excursion between S and T. And this property is exactly saying that S and T correspond to the endpoints of an chord drawn below the graph. Okay? And then you identify S and T, so you take the quotient space of the interval 0 sigma for this equivalence relation. You equate with this metric, it is not it's only a pseudo metric on 0 sigma, but if you define it on the quotient space, it becomes a metric on this quotient space. And in this way, you get the Brownian tree. Okay? So it is that saying that d of st equals 0 is the same as saying that s is equivalent to t. Okay? So this makes sense. Okay, so this is a formal definition of the Brownian tree. And I have repeated the definition here. And what we get, so we have this space TE equipped with the metric DE, we get a compact R tree. So what does it mean that it is an R tree? Well, you should really think of it as a connected union of line segments, say in the plane, for instance, which is a tree in the sense that you have no cycle, of course. Okay. And more formally, saying that it is an R tree means that if you have 2 points A and B in TE, there is a unique path from A to B, a unique continuous and injective path from A to B up to reparametrization. So in my picture, it's a blue path here. And the distance between A and B has to be the length of this blue path. Okay? But for what I'm going to say, you could imagine that you have such a connected union of line segments. Because the range of this blue path is what I'm going to call the line segment, if you want, between A and B. It is, in fact, isometric to a line segment. Okay. So some more notation. You can, of course, introduce canonical projection from 0 sigma onto the quotient space here. And you decide that you root the tree at point rho, which is defined as a P of 0. It's the same. It's obvious that 0 is equivalent to sigma in this quotient space. So it's the same as P of sigma. Okay. And you can also equip the tree with a volume measure, which is just a push forward of Lebesgue measure on 0 sigma under this canonical projection. So here I need to make a comment. Of course, you may condition the excursion to have duration exactly equal to 1. Okay? Then the tree that you get is just what is called the CRT, Aldous CRT, up to maybe a multiplicative constant 2, which is unimportant. Okay? But here, well, I'm going to deal with a setting where you do not condition on the duration. So I really work under this Ito measure n plus of dE, meaning that I work with a free excursion. I don't condition on the length of the excursion. And there are good reasons for that. In fact, the results will be nicer under n plus of dE. And also, if you think of applications, we'll mention some of the applications later, often it's useful to have other conditionings of n plus. Not conditioning on sigma, but for instance, conditioning on the fact that the height is greater than some constant. Okay, so this was a remark. Okay, so now I need to define a Brownian motion indexed by the Brownian tree. So again, informally, if you condition on the Brownian tree, you can define the same definition as Brownian motion indexed by the half-line, if you want. Okay, it's a centered Gaussian process, which is 0 at the root of the tree, and such that the variance of the increment between 2 points A and B is just the distance between A and B. Okay? So if you think of Brownian motion indexed by the half-line, it's exactly the same definition. Okay? There is a small technical difficulty due to the fact that here you have a random process indexed by the random set, because the tree itself is random here. But in fact, the tree has been constructed as a quotient space of 0 sigma, so you can as well view this process Z as indexed by the interval 0 sigma. So you are back in the usual setting, in the familiar setting. Okay? So this corresponds to what people call the Brownian snake construction here. Okay. So Z has continuous sample path, remark. In what follows, I will view ZA as a Brownian label, or you can think of it also as a spatial position, assigned to the point A of the tree. Okay? And the key property is that when you move along a line segment in your tree, your labels evolve like linear Brownian motion. This, in some sense, characterizes the process Z. Okay. Maybe I should stop at this point. There are no questions about what I'm introducing? Yes, there is.
Is it real valued or is it valued in?
Is it?
What's the space where Z is valued?
Oh, it's a one-dimensional. Okay, good point. Gaussian process, I mean, it's really one-dimensional, okay, with values in R, okay? But of course, you could also define d-dimensional Brownian motion instead of one-dimensional. This is one-dimensional if you want. And for applications, often it's a multi-dimensional version, where you have, instead you have a Gaussian process with values in Rd. And instead of writing that, I would write a covariance matrix will be the distance times the identity matrix. Okay? But in this lecture, it's going to be one-dimensional. Okay, maybe I will spend some time explaining this picture, which is it's a very naive picture, but I think it helps understanding what I'm going to do later. I think that, okay, so what I've represented here on the right, this is a tree, viewed as a connected union of line segments, if you want, the root at the bottom. And on the left here, I've tried to represent the labels or the spatial positions, if you want. So you should realize that the value of the label corresponds to the horizontal coordinate, the A here. The vertical coordinate corresponds to the distance between the root and the point I'm considering in the tree, the point A here. And in this way, you get the kind of tree of Brownian path. Of course, my picture is very much misleading because all these Brownian paths, they should intersect a lot and so on. Okay.
It's not the same tree. It's not based on the red tree.
It's based on the red tree, yeah.
Topology, you must look at that.
You mean my picture is not good? It's not a simulation. It's drawn by hand. No, I'm going to explain that. The genealogy of this tree of Brownian paths is prescribed by the tree. Okay? So it's the same genealogy. I've tried, you see, this point here, it's a branching point. It corresponds to this one if you want. But okay, it's only a bad picture. Okay, so what I was saying is that if I was using a simulation, all these paths should intersect a lot. Okay, but in my picture they don't intersect because it's clearer this way. Okay. Okay, so how do you get this tree of Brownian path? Well, suppose you consider one point in the tree. Here I've taken the point A1 here, and I want to construct the label of A1, so the ZA1 here. Well, what I do, I look at the line segment from the root, or the ancestral line, if you want, of A1, the line segment from the root to A1. This is the black segment here. You can see it black. And along this line segment, the labels evolve like linear Brownian motion. Okay, so this corresponds to the black curve here. This should be the graph of a linear Brownian motion. Remember that the positions, the spatial positions are represented horizontally. Okay, so the time is vertical here. Okay, and so this is supposed to give you the evolution of labels. And at time, which is the distance from the root to A1, you get the spatial position of A1. Okay? And you can generate in this way all labels, all spatial positions. So if you take another point A2, for instance, this point here, well, the same, you look at the ancestral line of A2, the evolution of labels along this ancestral line is given by a linear Brownian motion up to a time which is a distance between the root and A2, and there you find the label of A2.
Okay, then I'm able to ask my question because you were covered.
No, I've not finished. Just 1 second. I want to say that the green path is the same as the black path up to that level, which is the time at which the ancestral line becomes different, of course. But then the green one and the black one are independent.
Yeah. Okay, you have the first branch, the first blue branch, not yet colored. Okay. On the left.
Yeah.
And that's branching into 3, and I can't identify that with to a branch on your end.
It's because my picture is bad, I suppose, yeah. But you understand the model.
I understand.
That's the most important part. Don't pay too much importance to the picture, yeah? Just to give you an idea. Okay. Okay, so maybe before I continue, some motivations for that. So both the Brownian tree and Brownian motion indexed by the Brownian tree. So as I said in the reply to a question, you have to look also at multidimensional versions of those. But it's basically the same object, special positions are given by now Brownian motion in RD. You find that in many applications, so I will give a few of them. In particular, well, for asymptotics, for many combinatorial models, of course, you know, you can take asymptotics of random discrete trees. You can also look at embedded discrete trees, meaning that you have assigned also labels to the vertices. So people have studied that a lot, starting with the work of Eldus in the beginning of the 90s. But there are many other combinatorial models for which the asymptotics involve precisely these objects, both the Brownian tree and Brownian motion indexed by it. Okay. And of course, I mentioned also that it is a scaling limit of critical branching random walk. And of course, motivation comes from the general theory of super Brownian motion. Okay. This is not really an application, by the way, because it's really the same object. You can construct super Brownian motion from a Poisson collection of copies of this object, the Brownian tree and the labels on it. Okay. There are applications to interacting particle systems. So this, in fact, I mentioned here the work of Cox, Dorret, and Perkins, which gives scaling limits for the contact process. They're in terms of super Brownian motion, but as I said before, it's basically the same object. And there are also some applications for the Vaughter model. And there, in fact, one uses really the Brownian tree, which I have introduced, under conditioning, which is the height is greater than something. Okay? So different conditioning than the one leading to the CRT. Okay, and while there are applications to models of statistical physics, for instance, work of Derbez and Schleid on lattice trees, also to percolations, clusters in high dimensions. So we saw yesterday, I think in the talk by Bruno, the analogy between percolation clusters and branching random walk. So it's not maybe surprising that scaling limits of percolation clusters will again involve the same objects here. Okay, mentioned also oriented percolation. And of course, these objects, Brownian tree and Brownian motion indexed by Brownian tree, are also the building blocks for constructing the models of random geometry, the Brownian sphere, or I will not talk about this, but this is really the objects you need to construct the Brownian sphere or the Brownian disk, models like this. Okay, so let me come to local times now. So I consider the objects I've just introduced, Brownian motion indexed by the Brownian tree. And now the occupation field O is simply defined in this way. So it's the push forward, if you want, of the volume measure on the tree under the mapping A gives the label of A. Okay? So this is just your usual occupation field of the process of labels. Okay? And okay, again, a remark on the fact that you may condition your Brownian tree to have a total volume equal to 1. This amounts to saying that the length of the excursion is equal to 1. Okay? And then what you get for this occupation field is precisely the random measure which was introduced by David Aldous under the name of ISE, integrated super Brownian excursion. So this is just, if you want, a kind of free version of ISE. Okay, so an important fact is that this measure O has a density with respect to the Lebesgue measure. So this is, of course, what I'm going to call the local times here. But things are smoother than in the classical setting of linear Brownian motion. You know, in the classical setting of linear Brownian motion, local times are not differentiable with respect to the space variable. Okay? Here, the density is even differentiable. It's the fact that you have this branching process of Brownian path gives you a smoother local time, and it is differentiable. So the derivative will be denoted by L dot x. Okay? So natural to call Lx the local time at x. In some sense, it's a measure of the size of the set of points in the tree which have label x. Okay? Another question? Okay. So if you think of the classical Renite theorem, the one I mentioned before, it is natural to ask about the Markov property of the process of local times as a function of the space variable. So I say clearly, this is not a Markov process, okay? And I say clearly, but it took me a while to realize that because, okay, I had not noticed this differentiability property. But essentially, it's not a Markov property because of the fact that it is differentiable. Okay? It's very easy to understand. Suppose you fix some h, positive, you want to understand the future, well, I mean the value of local times for x greater than h, from the past, local times for x smaller than h. And if you want to make this prediction, well, it's not sufficient to know the present, to know LH, which would give you a Markov property. Why? Because certainly you also need to know the derivative. Okay? If you know just the value at h, if you don't know the derivative, you see the past give you more information. The past will give you the derivative, of course. And the derivative is needed in addition to the present. Okay? So it's more or less obvious that it's not a Markov process. But the nice thing is that you take the pair consisting of the local time and its derivative. This is a time homogeneous Markov process. Okay? So here I've taken positive values of x, and I will restrict to these positive values simply because of the fact that you have a symmetry property. Okay? If you look at the negative values, meaning this process, it has the same distribution as the one for positive values, and they are in fact conditionally independent given the value at 0. Okay? So here, again, you may have noticed that this Brownian tree is defined under an infinite measure, but essentially you can still make sense of this Markov property. You can, for instance, condition on an event of finite measure, like the event of where the local time at 0 is at least epsilon, and then the result makes sense. Okay. But it's only a technical detail. Okay, so what I want to explain now is that this Markov property can be understood from a certain excursion theory for Brownian motion indexed by the Brownian tree. This is similar, in fact, to the classical setting. You can prove the Renite theorem using excursion theory. Okay? And here it will be the same for this more complicated object, tree indexed to Brownian motion. Okay, so I will spend some time explaining this excursion theory. So this is the same picture. It's still very bad, but okay. I hope it will give you some ideas of what's going on. So I still have the tree here, TE, and representation for the labels is a collection of a tree of Brownian paths, if you want. Okay, so what I'm going to do, I'm going to look at excursions above level h here. So h is fixed, if you want. I will fix this value of h for the remaining part of the talk. And the same definition as the usual excursions of linear Brownian motion. I look at the connected component of the set of points in the tree where the spatial position is greater than h. Okay? So you should imagine here that I have drawn 3 such components here, the red ones. I don't know if it's very clear. And for instance, this big one here, C2, corresponds to the spatial positions which are here. And you see all these spatial positions are greater than h. And in addition, if you pick 2 points in the tree, and if you look at the labels along the line segment between these 2 points, they also stay greater than h. Okay? So this is because it's a connected component. Okay, okay, so you can make sense of these connected components. And of course, connected component in a tree, this will again be a tree. And I can equip them also with labels. So this is what I'm doing. The excursions of the above level h, these are the components Ci, so the red components if you want, equipped with the labels, the same ZA as before, but restricted now to Ci. So I can view them as R trees, compact R trees given with labels. Okay, so to get compact object, I need to take the closure, in fact. I need to add the points on the boundary, if you want, of the components. Okay, okay, so these are the excursions. So it's not the best mathematical way of defining them, but for the intuition, I think this is better. Okay, and something that's going to be important is that each time you have an excursion, you can define its boundary size. Okay, so how do you define it? You say that the boundary size of Ci is obtained by looking at the volume of the set of points in Ci, which have a label between h and h plus epsilon. You normalize this by 1 over epsilon squared. You take a limit. This gives you, well, of course, one has to prove that this exists, but this gives you what I call the boundary size. So here on this picture, I've represented, say, an excursion above h to this tree of Brownian path. And essentially what I am measuring for the boundary size, I'm measuring how many red points I have here, how many points, well, the size of the set of points in my excursion with label exactly equal to h. Okay, so if you want, these are Brownian paths. Okay, not exactly Brownian paths because they start from h and they stay above h for a small time interval. If you want. But basically, then they behave like Brownian paths. Some of them will come back to h. Then they are frozen if they come back to h. Okay? And I look at how many points I have here on the boundary. Okay? How many? It's in this sense, in the sense of okay, kind of a local time measure again. Okay? So that's going to be important.
Can I just check? Is this actually different from the local time at h of this?
Yeah, that's very different. Yeah, because it's just. Like here I'm looking only at one excursion. There are many of them, infinitely many of them, in fact, and there are points which have label h, which are not in the boundary of an excursion. It's the same for linear Brownian motion. If you look at points at which the Brownian motion is equal to 0, there are many such points which are not endpoints of excursions. The endpoints of excursions, there are countably many of them. The 0 set is uncountable. Okay. So here it's the same. Okay. So here, if you want, you get points that contribute in some sense to the local time at level h, but it's far from all points.
But I was wondering if this boundary is equal to the local time of h just restricted to the component.
No. No, it doesn't make sense. No. You would, okay, I understand what you mean. You would look at the local time measure evaluated on this set of points or something like that. But no, it does not work because it would be 0.
And the scaling 1 over 8 epsilon square would be the same in dimension.
Oh, this epsilon square, why? That's your question?
This is for any dimension. And what?
You mean, no, the process Z is one-dimensional here in this lecture. Okay. No, I'm not defining that in higher dimensions. Yeah. Higher dimensions, it's complicated.
Was this indicated that this set will be uncountable?
No, you're right. This set is uncountable, in fact, yeah. Yeah. But, okay, it doesn't matter. If you define it the object like this, yeah.
If you sum the boundary sizes for all boundaries, you obtain infinity?
Yeah, you're right.
So that's actually the issue, right? It's because there are two ways of measuring the local time of h, and this one just gives you infinity.
Okay. Yeah, it's a good point. You're right. I will mention that later, in fact, if I have time. Okay, so here's the following fact, which was obtained in a paper with Céline Abraham. Essentially, what happens is that we condition on all boundary sizes, then the excursions become independent. So it's very similar to what I recalled at the beginning of the lecture for linear Brownian motion. And for each excursion, you can describe its conditional distribution in terms of a probability measure, which only depends on the boundary size. Okay, I don't know. So there are two things in this statement. If you want, you have independence of the excursions once you condition on their boundary sizes, and the conditional distribution is given by a probability measure that depends only on the boundary size. Okay, so I have introduced here measures which I denote by n star zh, which correspond to the law of an excursion above level h with boundary size z. Okay, and I have fixed the boundary size. Okay? So this is maybe the basic result of excursion theory. Of course, just one remark, I have considered only excursions above H, but you can also consider, of course, excursions below H, and you have similar results. Okay? But I will be interested mainly in excursions above the level H. Okay, now if you want to get the Markov property of this process here, well, essentially because of this independence property between the excursions, what you really need to verify is the fact that if you look at the conditional distribution of the collection of DCI, these are the boundary sizes of excursion above level H. Given everything that is below level H, I don't say that more precisely, this only depends on this pair, the local time at level H and its derivative. Okay? And once you know that, you get the Markov property. Okay? And it turns out that this is true. And to state the result precisely, I need some notation. I will introduce this process, UBR-TY. This is a bridge of a Levy process. Okay, so it's a stable Levy process with index 3/2, with no negative jumps, there's only positive jumps. But it's a bridge because I condition it to be at y at time t. And I look at it only on the interval 0t. So why is this object relevant? Because you have the following key lemma saying that if you look at the conditional distribution of the boundary sizes of excursion above H, this DCI here, knowing well everything that happens below H, here I condition on the local times below H. This only depends on the pair LH and its derivative at H. Okay? And moreover, you can identify this conditional distribution. You impose that the local time is t and its derivative is 2y. This will be the sequence of jumps of the bridge which I've introduced above. Okay? So from this lemma, one immediately gets the Markov property of Lx and L.x. So if I have time at the end of the lecture, I will try to explain why we get this conditional distribution. Okay. Now let me come to the stochastic differential equation. Okay. So there is a very natural question. In fact, 2 years ago in our welfare, I mentioned the beginning of the results I'm talking about, and in particular the Markov property. And Martin Eirer asked me, well, can you say more than the Markov property? Can you characterize the law of your process in some sense? Can you describe it? Okay. And in fact, this is a joint work now with Ed Perkins. It turns out that we can obtain a stochastic differential equation for this process of local times and their derivatives. So more precisely, the pair Lx L.x satisfy this equation. The first one is just saying that L.x is a derivative of Lx. Still, I've written it to remark it, to recall it. But the second one is an interesting part, and it says that you can write the derivative as a solution of an equation of this form. And you see, this is very similar to the square root we already had in the Redite theorem I recalled at the beginning. Okay? And in fact, my first guess, when I started to work on this, my first guess was that you had only this first term and not the second one. But in fact, we do have the second one, which is a bit complicated, but which is written here. This function g of ty is described by this formula in terms of the density at time t of the same Levy process as I was mentioning before. Stable Levy process with no negative jump and index 3/2. Here I've characterized it by its Laplace transform, in fact. Okay. And okay, so of course here P prime t is the derivative of pt with respect to the variable y. Okay. So you get this equation, and so it's quite similar to the one I mentioned for the squared Bessel process, but you should notice that here the square is the square root of Lx, not of L.x. So it's really an equation that mixes Lx and L.x. Okay. Maybe I could mention there is a related paper by Chapuis and Marquet who started from discrete models and tried to get a similar stochastic differential equation for local times of ISC. Okay. But ISC is the model that you get when you condition on the total volume of the tree equal to 1, meaning that you condition the total volume is just the integral of Lx with respect to Lebesgue measure, integral of Lx dx. Okay? And you see that if you condition this equation, well, if you add another constraint, which is the integral of Lx equal to 1, well, this will, of course, destroy the equation. You will get something which is less nice. But presumably, one can still treat the case that was considered the local times of ISE from this equation, but I have not done that. Okay. Maybe I will go faster here. This is just to say that you can express the density Pt of x, and so therefore also the coefficient g, in terms of the classical Airy function. In fact, Pt is just a rescaling of this function, capital A, defined in terms of the Airy function Ai. And the function, this function A here is in fact also known in the literature. It's called the map Airy function in the book by Flajolet and Sedgwick. And so basically the function g coincides up to rescaling factor with the quotient A prime over A, which has this expression in terms of the Airy function. But maybe I will not spend too much time about that. Okay, this is also, I will go quickly here also. This is just to mention that you have the same result if you look at local times of super Brownian motion. Okay, you take one-dimensional super Brownian motion, starting at the Dirac mass at 0, look at the total occupation measure, this object. It has a density which can be chosen to be right continuous. It has a discontinuity at 0, but you can take it to be right continuous, and it is then continuous differentiable on 0 infinity. And the derivative of the density satisfies the same equation as before. It's essentially the same result as before because of the connection between super Brownian motion and Brownian motion indexed by the Brownian tree. It's not something new. Okay, maybe I will explain in this part how one can obtain the stochastic differential equation. Okay, so unless there are questions at this point, yes.
Just conceptual, like just say super Brownian motion. Like, what is super? This is like the
Oh, it's a measure of
space or the base space. What is super?
Okay. Okay, it's a classical object. It was very classical 20 years ago, but now it is less, I think. It has been studied much, in fact. It's a scaling limit of branching particle system, branching random walk. Like a suitable branching limit of, suitable scaling limit of branching random walk. You get a measure valued process, and which is called a super Brownian motion. And it has been studied a lot, and but this is not very different from the objects I've introduced, except that what you need to consider, for each time, okay, maybe it's a bit too long to explain. Essentially, in my tree of Brownian paths, you have an underlying time, which corresponds to the distance from the root in the tree. And essentially what you do, you look at every t, you look at the set of positions of your particles or your path, if you want, at that time, t. And there is a natural way of defining a measure of the set of positions, set of labels, if you want. And as t varies, you get a measure valued process. This is super Brownian motion. Okay, but I don't want to spend too much time on that. No other question? Okay, so this is the key lemma I stated before. This was a key lemma giving the Markov property. And in fact, we can use this key lemma also to make explicit calculations. Okay, so essentially, okay, I'm going to give a name to the sequence of jumps of my Levy bridge here, which corresponds to, this sequence of jumps corresponds to the distribution of the boundary sizes of excursion. And I want to compute the expected value of, okay, here I look at the derivative of local time at level h plus delta, knowing the local time at level h, and knowing its derivative at h. Why am I interested in that? Because I want to obtain a stochastic differential equation. So this, if I understand the behavior of this quantity, this will tell me what is the drift in my stochastic differential equation. So how can we compute this? Well, we just, for equality, I have just written this derivative as the sum over the connected components above level h. Okay? If you want, I separate the contributions of all the excursions above level h, which are these CIs. Okay. Okay. So the derivative will be the sum of the derivatives here. And then I use a lemma saying that I know the distribution. Okay, first I know the conditional distribution of the excursions. They are given by these measures n star z h, where z corresponds to the boundary size. Okay, so but I know also the distribution of the boundary sizes. This is the same as the sequence zi. Okay, so what I do here, I say that if you want the contribution of the ith excursion, well, its expected value can be written as that if I condition on the boundary size. Okay. So this is essentially a straightforward consequence of the key lemma. Okay, so I've written the same equation here, and it turns out that there is an explicit expression. So I found it in a previous paper with Armoriera, for not exactly this quantity, but for its derivative. Okay, this is the formula I've written here. And this involves a function chi, which is explicitly written in this way, but it's better to think of it as in terms of its Laplace transform. The Laplace transform of chi is just 1 plus square root of lambda minus 3, okay, to the power minus 3. Okay. But we are not really interested in this object, but in this one where we have the derivative of the local time. So essentially what we need to justify, we need to take the derivative with respect to delta here, okay, to get the derivative of local time. Okay. And of course there is a problem of interchanging the integral with respect to this measure and the derivative, which is not trivial in fact, but it can be done. And if we differentiate the right side here, we arrive at a formula for the expected value under this measure n star ch. I remind you that this is the law of a Brownian excursion, of an excursion of my process with boundary size z. And you get an expression in terms of another function gamma, which is closely related to chi, in fact. Okay, so this is not so important, these are calculations. Important thing is that we arrive at this formula here. Okay, here what I have done, I have just taken formula that was above and replaced this by the formula here. And then the i's are the jumps of the Levy bridge. Okay, and when I arrived at this formula, I thought, well, I'm not going to be able to compute that because we know very little about the distribution of jumps of a Levy bridge. Okay, so I discussed that with Jean-Bertrand, and he said to me, well, no, we don't know the distribution for the bridge. Of course, if it's a Levy process instead of the bridge, it's very easy. It's just a Poisson measure. Okay, but for the Levy bridge, we have very little information. But still, the miracle is that we can compute what is above. We can compute this quantity, and we arrive at a formula like this. So here I have subtracted the value of the derivative at h. So I take the difference between the derivative at h plus delta and the derivative at h. And I condition of this, it simply means I subtract y here, okay, or 2y. Okay. And we get a formula like this. It's a miracle, which involves, in fact, the density of the Levy process, Pt I introduced before. Okay. And this is nice because you see you have an increment of the function pt here between y and y minus delta square z. We normalize by 1 over delta, but we are also going to multiply this by 1 over delta. And so you will see here appearing the derivative of pt with respect to y. Okay, that's what I've written here. And so this tells you that when you take the limit as delta tends to 0, you get the derivative here. You get this pt of y, you get t, and you are left with an integral which you can compute. Okay? And then you arrive at the function g I introduced, which was giving the drift in my stochastic differential equation. Okay, okay, so this is going to, once you have this, this is going to give you, if you want, the drift in your stochastic differential equation. Okay, you look at the expected value of the increment of the process on a small time interval, h plus delta, you normalize by delta. This corresponds to the drift in your equation. Okay, so more precisely, what you get from this calculation is that if you subtract to the local derivative of the local time the integral of g applied to the local time and half the derivative, say, from 0 to h, you get a martingale. Okay, this really follows, well, there is some work, of course, to be done, but this really follows from this property here. Okay, so then you have obtained, if you want the drift, you arrive at a martingale, and you need to obtain the diffusion part. And for this, we have used a result obtained by Hong, in fact, he was a student of Ed Perkins, which was for super Brownian motion, but in fact, it carries over to our setting. It's really the same object. And this is telling you that if you take any sequence of subdivisions of 0h of mesh tending to 0, and if you look at the sum of the squared of increments of the local time, or the derivative of the local time along the intervals of this subdivision, this converges towards a constant 16 here times the integral from 0 to h of Lx dx. Okay, so this was already known, and this will give you, in fact, now the quadratic variation of this martingale. Okay, from this result, you can infer that the quadratic variation of this martingale is what we get here. It's a classical approximation for the quadratic variation of a martingale. I should say a continuous martingale. Okay, so you have obtained the quadratic variation of the martingale, but this is telling you, if you want, that you can represent the martingale as an integral of this time with square root of Lx in the Brownian motion. Okay, and you have this equation and this one, and this exactly gives you the stochastic differential equation. So do I have time? I still have some time. There's a question? Yeah?
No, sorry. You said the time is there.
The time left is written on the board. 8 minutes. No,
On the screen.
the screen.
Oh, 8 minutes. Thank you. Nathanael?
Is it obvious that there is a unique solution to this problem?
To this equation? No, but it works because you know how. Okay. No, that's a very good point. Yeah. No, it's not obvious. You have to work for that. Yeah? No, because it's not a one-dimensional stochastic differential equation. Well, there are ways to rewrite this equation in a simpler way to get back to a one-dimensional equation, and then you see that you have a uniqueness, but you have to work here. Yeah? The way I've written it, it is not clear.
So can you explain a little bit more about this magic? You said that a priori it was not clear that you could compute this explosion.
Yeah. No, I think I cannot do that. I should have prepared it because
But is it because inside the expectation there is also something that is very special and depends also on the study process? Or?
There are Fourier techniques, in fact, involved in this calculation, but I don't remember exactly. Yeah.
So if I change my function inside the expectation, a priori you would not be able to compute that.
Yeah. Yeah, there's some magic here, but it's complicated to explain it here. And I'm not sure I can do it just right now. I will have to look at the paper. Okay, so in the last few minutes, I will try to give some ideas of the proof of the lemma. That's going to be a bit technical. I'm sorry for that. I apologize. So I already said all that. It's just to remind you of the notation. H is always fixed. You know what I'm doing. Okay, and this is the key lemma I stated before. So basically, well, you can introduce a sigma field that corresponds to what happens below H, essentially generated by the excursion below H. And you also have to consider the path when they all start from 0, you know, the path, but before they hit H, okay. And then the local times for values of R here less than H are measurable with respect to this sigma field, and in particular, the derivative is also measurable. You only need to know that to know the derivative here, okay? So essentially, what you need to show is that the conditional distribution of the boundary sizes given the sigma field FH is as described here, okay? I'm not going really to do that because, but I'm going to explain how you, why if you condition on the local time and its derivative, why you get this precise distribution, sequence of jumps of a bridge. Okay, so there are several facts. The first one is that the boundary sizes of excursions, alors here I take all excursions, both below and above h, and you can find them as the jumps of a certain continuous state branching process X with a stable branching mechanism. So maybe I have no time to explain what I mean if you don't know what this is. But essentially, continuous state branching processes are continuous analogs of classical Galton-Watson branching processes. And the distribution is characterized by a branching mechanism, which is a function psi I've written here. Okay. Of course, this is analogous, in fact, to what I mentioned before. The length of the excursions was the jumps of a stable Levy process. Okay, so how is this process capital X obtained? Essentially, what you say that for every S, you have a way of measuring the size, and not too precise here, of the set of points in your tree, which have label H, okay? And you have an additional property that the total local time, here I'm speaking about usual Brownian local time. The total local time accumulated by Z along the central line of A is equal to S. Remember that the labels will evolve like a linear Brownian motion along a line segment, in particular along an ancestral line. So it makes sense to compute the local time accumulated at H by the labels. It's just a classical local time here of linear Brownian motion. For S equals 0, in fact, you measure the size of the set of A such that they have label H, and all their ancestors have a label smaller than H. Okay. First sitting term of H if you want to. Okay. Now, the property I'm going to use is the fact that the local time at level H turns out to be the integral from 0 to infinity of this process XS. It's not too much surprising because I integrate over all values possible for S here, and then I get all points such that ZA equals H, and the measure of the set of points is just the local time at level H. Okay, so this is just I'm reminding you of the property of the boundary sizes. Now, when you have a continuous state branching process capital X, you can write it as a time change of a Levy process whose Laplace exponent is the branching mechanism. Okay. And from this time change representation, you get that the local time, I told you before, it's just the integral of XS with respect to ds, is the same as the healing time of 0 for the process Y. So I need to introduce one more object. So the jump of Y are the same as the jump of X, so they correspond to boundary sizes of excursions above or below. Okay. Now I can consider a Levy process, which is obtained by keeping only the jumps of Y corresponding to excursions above level H. So its Laplace exponent is just 1/2 of the one for Y, so it's just psi of lambda, and I take the initial value 0. Then by definition, the boundary sizes of excursions, is what I'm interested in, are the jumps of this Y plus between 0 and T0. Okay, I'm going to condition on LH, I mean I'm going to condition on the terminal time to be equal to something, this T0, and also on the derivative. And, well, last minute. So I just, fact 1 I already mentioned. So fact 1 gives you a representation of the local time at H. And factor 2 gives you a representation for the derivative of the local time at H. And it turns out that this is the same as the value of the process Y plus. I kept only the jumps corresponding to excursions above level H. And so half of the derivative at H is equal to Y plus at time T0. And it's very easy to see, 40 seconds. You look at this expression. It's quite easy to see that it converges to 1/2 of the derivative of the local time. It's very easy. And on the other hand, if you look at the first part, you can decompose it according to the different excursions. And then this quantity behaves a little bit like the sum of the boundary sizes of excursions. But as it was mentioned by Antoine, I think, this sum is infinite. So, but this corresponds to the fact that there is a renormalization here. And in fact, you can renormalize this quantity here. If you put this quantity here, this means that you are going to renormalize the limit. and this gives you the process X plus T0. Okay? And that's finished. Once you have these two facts, you can see that the conditional distribution of the collection of boundary sizes, it will correspond to the sequence of jumps of the process Y plus, as I said before. But on the time interval 0t, because LH corresponds to capital T0, and conditional on the fact that the terminal value of Y plus is Y, this is because of the second fact here. Okay, so, sorry, I was too long. Thank you for your attention.
Thank you. Any questions?
So how can we see how the exponent 3/2 comes up? So compared to the 1/2 of the standard one.
Yeah, so there's something I wanted to explain on this picture, but I have no time. Roughly speaking, it's the same picture. I've put some excursions here, the red ones. What you can do is the result saying that you can glue all these ray parts, all these excursions, they are above and below level, into a single point. And if you do that, that's so clear on my picture, if you do that, you will get a tree which will no longer be binary. This one is binary, in fact, I should have mentioned that, but a tree where you have very points with many descendants. Think of, you have glued all this into a single point. You see you have one descendant here, one descendant here, one descendant here, and in fact you will have infinitely many of these. Okay? And this tree that you get by this gluing operation is a stable tree with index 3/2. Okay? And when you have a stable tree with index 3/2, when you have such nodes here where you have many descendants, each node corresponds, if you want, to an excursion, but you can define also the size of the node, and this corresponds to also to the boundary size of the excursion. Okay, so just another way of looking at that. But the 3/2, I mean, I have no good explanation except what I was saying. There are other research which tell you that you get stable 3/2 mechanism for related objects, in fact. But here, you see it's not hard to see that the nodes, they correspond to jumps of the continuous state branching process. And so the fact that you have a stable tree with index 3/2, this means that your continuous state branching process has also a stable branching mechanism with index 3/2. Okay, Amine d'abord, après.
Is there a critical branching random walk for which you have your main theorem that of the time and its derivatives are Markov process?
That's a good point, yeah. It's interesting. If you take discrete models, you mean you can start from a Galton-Watson tree, critical of-string distributions, finite variance, and you put displacements that you can put, for instance, -1 or +1 with probability 1/2. So it gives you a branching random walk, and you can ask, well, is the process of local times? Local times are just how many points you have with a given spatial position, okay? And is it Markov? Okay. And I've been thinking of that, and in general, it does not work. It works in the limit. But there is one special case where when it works, it's the case when you have a Poisson of string distribution. Okay? Because then, because of the property of the Poisson distribution, the number of children, if you want, of an individual that go to the right and the number that go to the left are independent. And you can use that to get, it's not completely obvious, but you can use that to get a Markov property of local times. Okay? But you see, here this object is a kind of universal scaling limit for many different branching random walks. But it's enough to see that you have just one discrete model for which you have the Markov property. It passes to the limit. Okay? But the other discrete models, I think, it does not work. Okay? It's a bit, well. But it's a very good question. I've been thinking of that. Yeah. I've been thinking also about deriving the stochastic differential equation from the discrete models. But I think people have to be very smart in combinatorics to do that. Yeah. Maybe it's possible. Daniel?
Yeah, I wanted to ask about the form of this drift, this P prime T over P T.
Yeah.
is a bit suggestive of maybe of an H transform type of thing. Is that? But obviously that's not how you derive it. But is that?
Yeah, that's a good point. Yeah, it's of course a kind of drift you can find in other settings, and yeah, surely, yeah, H transform. But maybe there is another way of seeing we must have this drift, but I didn't see it. Okay. In a sense, the drift it's not very complicated. Of course, if you look at the expression in terms of area function, but basically it's a derivative of this transition density for the Lévy process. The derivative of the density divided by the density. So it's not very complicated. Yeah. No, but I don't know how to answer your question. Oh, yeah.
So if I change my ground motion and I consider a baseline process,
yeah.
Is there any hope that some of these things will still work?
Yeah, I think that there is hope. Basically, I think this is certainly not the best general result. You can have more general spatial motions instead of Brownian motion. Yeah, many things should work. Yeah. I was primarily interested in that case because it corresponds to the applications I have mentioned.
So but the magic trick with the Lévy jumps.
I think many things should work. Yeah. Okay, I'm not completely positive about it, but I think true.
So you mentioned this connection with the Brownian sphere and so on.
Oh, yeah.
So do these results have any interpretation? In that
Yeah, sure. Okay. Yeah, and okay. Essentially, okay. So in the Brownian sphere, well, you have one distinguished point, and you know well the distances from this point, and so the local times there will correspond to the volume of spheres, not balls, spheres. Okay. So how can I explain that? Essentially, it gives you. Of course, it does not tell you that the process of volume of spheres is Markov. You have to add something, this derivative. The derivative corresponds, in fact, to a kind of... you see, spheres have many holes. I don't know if I can... You will have many holes like this. And essentially, the derivative will correspond, in some sense, to the sum of the sizes of the holes, of the boundary of the holes. Okay. And so you will have a Markov property for the volume of the sphere plus this quantity here. Okay. And what I've been trying to do recently also, and I think it works, is also looking at the Brownian plane, which is infinite volume limit. And there it's nicer. I think you can describe fully also the process of volume of spheres and derivatives. Okay. So yeah, it has an interpretation. Yeah, I've written that in the first paper, in fact.
Okay, so I think we should thank Jean-Francois again.